Hello everyone. Please note that this is a NotebookLM video presentation. Thank you NotebookLM. Hope you find it useful.
All right, welcome to The Explainer. Today we're going to dig into a really fascinating puzzle at the very heart of artificial intelligence. It's a story about how machines can see everything in a picture, but somehow understand almost nothing about what's actually going on. So check this out. You go to a state-of-the-art AI image generator. You type in a tiger chasing a rabbit, and boom, you get this stunning, perfect image. Simple. But then you flip the script. You ask for a rabbit chasing a tiger. And suddenly, this incredibly powerful AI just gets confused. It might draw the tiger chasing the rabbit anyway, or just kind of plop them next to each other. So what's happening here? Is the AI just being difficult? Or is there something much, much deeper missing from the machine's brain? You know, this isn't just some quirky little bug. Research from Shuhao over at UCLA shows that this exact failure reveals a fundamental gap. A gap between simply recognizing patterns and actually genuinely understanding the world. So let's dive in. Okay, so to be fair, modern models like DALL-E 3 have gotten way better. They can nail basic descriptions most of the time. But the research is clear. When you give them prompts that reverse the usual roles, like our rabbit and tiger, their performance just tanks. The same thing happens if you ask for scenes with multiple relationships. You know, something like a sphere is on a cube and that cube is near a cylinder. The AI gets lost. It's almost like it's not really reasoning about the scene. It's just repeating the statistical patterns it's seen millions of times before. And in its world, tigers almost always do the chasing. To really get why AI fails at this, we first need to appreciate a superpower our own brains have, something we do so automatically we don't even notice it. So what is this grammar of vision that we've all mastered, but machines just can't seem to learn? And that superpower is called relational reasoning. When you look at a scene, you don't just see a laundry list of objects, a person, a bicycle, a street. Your brain instantly computes the relationships between them. The person is on the bicycle, which is on the street. You can really think of it as the grammar of vision. It's the thing that turns a jumble of visual nouns into a coherent, meaningful sentence. And get this, we are unbelievably fast at it. Research shows the human brain can pick up on complex relationships like inside or chasing in less than 50 milliseconds. That is literally faster than you can blink. And the wild part is, it often happens before we've even consciously registered what the specific objects are. This automatic, lightning-fast process is a huge, huge difference between our perception and what machines are currently doing. Okay, so how do researchers actually measure this gap in relational reasoning? I mean, you can't just ask the AI if it gets it. Instead, they design these really clever tests that are specifically built to fool any system that just relies on matching patterns. One of the gold standards here is a test called Bongard-Hoy. The setup is actually pretty simple. The AI gets shown a few images that follow some kind of secret rule and a few that don't. Then it has to decide if a brand new image follows that rule. And here's the kicker. In this test, the rule is always a relationship. But the real genius is in how the test is structured. For a rule like a person riding a bicycle, the positive examples all show that action, of course. But the negative examples aren't just random images. They also contain a person and a bicycle. The person might be standing next to the bike, or maybe carrying it. This is a brilliant little trap because it forces the AI to look past the objects themselves and focus only on the relationship between them. It has to understand what riding actually looks like. And the results? Well, they're pretty stark. Humans are nearly perfect, scoring around 95% accuracy. The latest models, like GPT-4V, are a big step up from older AI, hitting about 77%. But that's still a massive gap. This just goes to show that even our most advanced AI is missing a core piece of visual intelligence. It can see the what, but it still really struggles with the how. So if just making bigger models and throwing more data at them isn't closing this reasoning gap, what will? Well, the research argues that the answer isn't more brute force, but more intelligence, specifically by taking a lesson from the original masters of vision, us. Most AI today is trained end-to-end. It's essentially a black box that looks at billions of examples and learns statistical correlations. It's powerful, yeah, but it's also brittle. It struggles when it sees something new. The alternative is a cognitive-inspired approach, where we actually build the principles of human perception right into the AI's architecture. It's like the difference between learning to cook by memorizing a million photos of food versus actually learning the recipe. One just mimics, the other understands the structure. And one of these key principles is something called hierarchical abstraction. When you see an object, you don't process every single pixel at once. Your brain first gets the big picture, the overall general shape. Then it zooms in on the finer details and the individual parts. This forest before the tree strategy is what makes our vision so incredibly robust, letting us recognize things from any angle, in bad lighting, or even when they're partially blocked. Now, this whole cognitive approach isn't just a theory. It actually led to the development of a new model that's designed from the ground up to reason about visual relationships through analogy, just like we do. It's called VisiPAM, a bit of a mouthful, I know. It stands for Visual Probabilistic Analogical Mapping. The best way to think of it is as a hybrid. It has the superhuman eyes of a modern AI for seeing pixels and shapes, but it connects those eyes to a brain built to think like a detective, always looking for connections, for patterns, for relationships. And here is the most incredible part of this entire story. To get VisiPAM to solve these complex visual analogy problems, the researchers trained it on exactly 0 of them. That's right, it learned how to recognize the parts of objects, but it got no training whatsoever on the analogy task itself. This is huge because it proves it's not just memorizing answers, it's genuinely generalizing its knowledge to solve a whole new kind of problem. This all points to a pretty radical shift in how we think about building AI. The dissertation puts it perfectly. It's not about making the models bigger, it's about making them smarter by fundamentally changing how they reason about the world. And that leaves us with a really provocative final question. This work suggests that for a machine to truly understand our visual world, to see a rabbit chasing a tiger and know that it's weird and funny and not just statistically unlikely, we might need to give it the same cognitive tools that we use to make sense of it all. So to build a true AI, maybe we first have to build an artificial mind.